Good. Okay, welcome back, everyone. We're going to have the second talk of the day from Natalie about complexity-theoretic lens on magic and quantum states. Take it away.
Thank you. Yeah, it's nice to be here. Hopefully people still have like some energy from the week. But yeah, today I'm talking about, thinking about magic from a complexity theory perspective. And I'll be talking about two papers, mostly this first paper, my paper on quantum circuit lower bounds in the magic hierarchy. And I'll also mention some cool results that also connect magic and complexity, and in particular communication complexity. And this one's joint work with Uma Girish, who was at Columbia as a postdoc and is now faculty at University of Toronto. Oopsie. Alex May, who's at Waterloo, and my advisor, Henry Yuan. So to first, since there's some physicists here, I thought I would throw up some physics things to try to motivate quantum circuit lower bounds. So quantum circuit lower bounds show up in a lot of different areas. So as we've talked about phases of matter in topological order, but they kind of prop up in problems in various areas of physics. And but progress is very challenging on these problems, and this is sort of because quantum circuit lower bounds themselves are very challenging. So in this talk, I'm going to focus on quantum circuit lower bounds for preparing states at first. And so what do I mean by this? You have some state psi, and you want to know like how hard is it to prepare this state. So you start with all zeros, you apply some sequence of gates, and we want to know how many gates are needed or how much depth is needed. And generally, you're allowed 2 qubit unit, like the gates are just 2 qubit unitaries from some gate set. They don't have to be acting on nearest neighbors. I've just drawn them this way in my slides because it's easier. But yeah, just to clarify, I allow like all-to-all connectivity in this talk. So now by a simple counting argument, it's well known that most states require exponentially large circuits. But nevertheless, it's hard to prove that any explicit state requires a large circuit. We can't do this for any explicit state, but we know, if you sample a random state, it has exponential circuit complexity. So why can't we prove stronger lower bounds? We know that almost all states require exponential size circuits, but we can't prove it for any specific state. So this sort of task is like trying to find hay in a haystack. Typically there's hay and a few needles, but all states are actually hay, but we still can't really like prove it for just one of the pieces of hay. But we're not dumb. This is like a fundamentally hard problem, and so this is something I'll talk about later in the talk. So what can we do? So the main existing technique that's used a lot is the so-called light cone argument. Now in physics, this is like the Lieb-Robinson bound. So this is a simple observation that in this circuit, output A is only influenced by the inputs in its backwards light cone L of A. And so in particular for these 2 qubits A and B, they can't be more correlated than their backwards light cones were LA and LB. And the size of these light cones is bounded by the depth, because the light cone size can double at each layer since the gates act on 2 qubits at a time. So in particular, if the depth is constant, then the light cone size is also constant. So now we can see pretty straightforwardly how to use this to get a lower bound for preparing a state. So yeah, consider the cat state uniform over all zeros and all ones. Now each pair of qubits is correlated, right? You measure one qubit, you know what the other qubit will be if you measure in the standard basis as well. So the light cone sizes have to be linear. They all have to all the light cones have to intersect. So this means that your depth has to be logarithmic. But now this argument no longer works if the depth is like greater than log n, or if you allow yourself some larger gates. So you have some gate that can act on many qubits at once. Now the light cone argument just tells you the light cones have size n, which doesn't restrict you at all. So we would like to go beyond the light cone argument. And so here I've sort of put up a bunch of like next generation, oh yes? I guess, oh, I hate how it does this. I guess like you can imagine you have a gate that can act on like n qubits at once, but maybe it's not a obviously powerful gate or anything. Like you can do a big Toffoli gate, for example. like control, not or something, yeah. As long as the gates are acting on a constant number of qubits, this argument still works, but if you have something that's like linear, it doesn't work. Yeah, feel free to interrupt with questions. Okay, so here I've thrown up a bunch of, these like next generation models of circuits that are, seen as potentially realistic to implement and in a sense, constant time, but they are able to do these more like global operations. So for example, you could consider like we've seen like, Clifford and T-gates, like, Clifford is kind of, in fault tolerance seen as very cheap. So, let's say you consider Clifford free and then you count how many layers of T-gates. You could consider these circuits that maybe are allowed certain certain gates that can act on many qubits at once. Or you could have like short time global Hamiltonian evolution, or circuits where you have they're constant depth, but you have like intermediate measurements and feed forward, which are like I'll call adaptive circuits. And so we don't have any lower bound techniques for any of these circuit models. And this is because kind of the light cone argument just doesn't work anymore. And in this talk, we'll start to understand why it's been so hard to prove lower bounds in this model. And we'll see that they're all, I won't really talk about this one anymore, the Hamiltonian evolution, but I wanted to mention it because it fits in this, it fits in this category. But we'll see that the rest are all like, equivalent in some sense. Okay, so now I'll give my talk outline. So first I'm gonna provide the landscape of quantum circuit complexity, what we know, what like mountains we can try to climb. I'll introduce a new circuit model, the magic hierarchy. And I'll show that this circuit model unifies the constant time computation models we saw on the last slide. I'll then show that there's this meta complexity barriers to proving circuit lower bounds for these models. And then I'll prove some lower bounds within like the first level of the hierarchy. And so that's sort of like the main part of the talk. And then I'll also, mention as well as from my other paper, I'll talk about circuits that they're Clifford with some T gates. And what we care about is bounding the T count or the T depth. And I'll show how you can get new lower bounds on T count and T depth from communication complexity. So yeah, good question. So meta complexity is like the study of how hard it is, like the complexity of actually proving whatever thing you want to prove. So is this thing like, oh, if you proved a lower bound and you took one of this very wide class of approaches, then this huge other implication, you break cryptography or something. So it's sort of saying like, you can sort of like, you can say a complexity statement about how hard solving this math problem is, like as a researcher, kind of, which is kind of cool. Okay, so now I can try to help us build a landscape here. So down in our valley, we have our light cone-based lower bounds. This is what we know how to do. Really well studied, not so kind of trivial. But what else is out there? What's at the top of this mountain? What are like some like approachable first hills to climb? So first, I want to say that these constant depth models are like really surprisingly powerful. Before we like place them on the mountain, I want to sort of convince you that they're difficult to prove lower bounds for. So let's consider the following circuit model. You have, arbitrary single qubit gates, but then you also have these large gates that can act on many qubits at once, and they're fan out. So they're basically classically copying bits, and like they're copying in the standard basis. So it's like control not. And yeah, surprisingly powerful. So Hoyer and Schwalik showed in 2005 that these fan-out circuits can be used to implement arithmetic circuits and even, our algorithms, bread and butter, phase estimation, and quantum Fourier transform, even though it's only constant depth. And more recently, myself and co-authors Ben, Fran, and Henry showed that you can implement pseudo-random unitaries with these fan-out circuits. Going back to state preparation, we can see that you can create globally entangled states with these fan-out circuits. So, for example, this cat state we're familiar with, it's clearly, just a Hadamard and then a fan-out gate. It's also, maybe many of you know as well that the toric code can be prepared by these circuits, and even some non-abelian anyons, in particular, like for the quantum double model for solvable groups. This was originally shown for a slightly stronger circuit model, but like looking into the proof, you can see that you can implement them with fan-out circuits. Okay, but now I actually want to pause a little bit about this. This is actually quite interesting that you can prepare these non-abelian anion. Oh yeah. Yeah, they use measurement and feed forward, but you can also do it with fan out.
I think people based on the measurement-based protocol, there are some states you can prepare that when it gets right. So
well, they conjecture that.
Yeah, conjecture. Yeah, they haven't proved that. What I'm asking is, can you say that using this kind of circuits, you can see do the measurement-based protocol on this kind of circuit do the same
Oh, like they're equivalent? Yeah, I'll get to them, like the equivalence between these two, yeah, later. Yeah.
Okay, so maybe I'm trying to bring what it's a little weird because it's like that unbounded fan.
Yeah, the thing is, yeah, I haven't really thought about locality. But yeah, the fan out doesn't, locality, I guess. I think if you have 2D locality, you can do, it doesn't matter. 2D and up is the same. 1D, yeah. I mean, I would need to verify, but like, I think once you can do 2D locality, you can do arbitrary. Yeah. Yeah, good questions. So yeah, what about why did it so you might ask, like, what about non-solvable groups? So maybe as like some of you are already thinking, yeah, there's this paper by Tantavasada, Karin Vishwant, and Vriesen, where they conjecture that if your group is non-solvable, the corresponding quantum double model can't be prepared by these fan-out circuits. I mean, they actually conjecture something stronger, that they can't be prepared by these adaptive measurement circuits, but implicitly they conjecture this. And from talking to people, in my experience talking to some people in this area, my impression is that this is somewhat just widely agreed upon. It's not proven, but they have some argument that people kind of accept. But I was a bit surprised to see this, and yeah, am a little bit, I guess, suspicious of the lack of rigor, because let's stare at this a little bit longer from the perspective of a computer scientist. So what are they saying? They're saying there's a specific state psi that these fan-out circuits cannot prepare. Well, there's this really nice result by Greg Rosenthal from 2023, where he showed that if you prove a lower bound against these fan-out circuits, that implies there's actually a specific function that can't be implemented by certain classical circuits, namely these constant depth threshold circuits. If you don't know what these are, it doesn't really matter. They're just constant depth circuits, and the gate you're allowed to do is like a majority gate, with with like unbounded inputs. The main takeaway from this that you need to know, though, is that a lower bound for TC0 would be a major breakthrough in classical complexity. So on one hand, we have that, this has been showing a specific function can't be computed by TC0 is just like a long-standing open problem. Lots of smart people have thought about it for a long time. But beyond that, we have this sort of like meta-complexity barrier. So there's this thing called the natural proofs barrier by Razborov and Rudich, where they show there's this really big class of proof techniques they called natural proofs that somewhat that at the time captured like all the proof approaches people had taken for classical circuit lower bounds. And they showed that like all of these proof approaches are destined to fail. None of them will work. And so if you want to prove a lower bound, you have to somehow come up with a non-natural proof. Right. And so this sort of, when I saw this, and also as a computer scientist, I didn't yet realize the difference in language between physics papers and computer science papers. And when they said like, we argue, I thought that meant like, we prove. And I was like, oh my God, like they don't know how famous they should be. This is a really big deal. And then, yeah, and I was a little bit frustrated. And then I learned that that's argue, it doesn't mean prove. Yeah. Okay, so let's return to our landscape. So down here again, we have our light cone based lower bounds. And I put up at the top these fan out lower bounds in proving the TVB conjecture. And I put it at the top because, in order to climb to the top and prove these lower bounds, you must have had to, along the way, climbed this other mountain where you prove TC0 lower bounds, which, again, don't worry about it too much. Just the takeaway is that this would be like a huge breakthrough, and you'd be quite famous, at least I don't know, in my circle. Yeah, and so this is sort of the top. And okay, I'll also mention one more problem that I've spent a lot of time on, and some other people have as well. That's the difference between QAC0 with fan out and without fan out. But if you're not familiar with it, also don't worry. I just wanted to mention it to sort of say, this has sort of just been the state of things. I worked on this for a long time, like first 2 years of my PhD, other people have too, and we've made progress, but we've kind of been stuck for a long time. And it's a bit frustrating because, this is sort of the main problem people have been working on that doesn't have like obvious huge barriers. I sort of felt like, okay, it would be nice if there was something else to do, another way to try to climb this mountain. I don't quite want to prove these things up here yet because, yeah, I don't want to be famous. But what if there was an easier way to climb this mountain? So, like a magic hierarchy. So, yeah, so next I'll introduce this thing called the magic hierarchy, which is a circuit model, but there's sort of like a sequence, it's a sequence of levels. And at the very bottom, the 0th level, contain circuits where we have lower bounds already for, like we can do the light cone based lower bounds, for example. And if you consider the whole hierarchy together, it's equivalent to these fan out circuits. So if you prove lower bounds for the whole hierarchy, you climb this mountain. But the hope is that, we can do it step by step. Okay, so now I can introduce the magic hierarchy. It's quite simple. It's just circuits that consist of Clifford components and constant depth circuits. And it alternates between the two a constant number of times. So if it alternates k times, we say it's in the kth level. But yeah, it alternates a constant number of times, like independent of the input size. So implicitly, we're talking about a family of circuits. Okay, the definition makes sense. Okay. And yeah, it's called magic hierarchy because we can think of the level of the magic hierarchy as like a gate set agnostic measure of non-Cliffordness or magic. Also, these constant depth circuits are also called QNC0. If I say that, that's why it's not a good name. Okay, so what are the two components, just to make sure we're all on the same page? So our constant depth circuits, or QNC0 circuits, are constant depth, arbitrary 2-qubit gates. Again, they are not necessarily geometrically local, even though they're drawn this way. And I'm going to allow them to be arbitrary gates, not fix a gate set. Since we're trying to prove lower bounds, this is the reasonable thing to do. We know lower bounds using the light cone argument. But Clifford circuits, they are allowed arbitrary size. That part's not bounded, so we can't use the light cone argument on Clifford circuits. But now what's restricted is the gate set. So the gate set is now severely restricted. You can only prepare stabilizer states, which is a very discrete class of states. So these two circuit models are very prolific and studied. All of you have dealt with Clifford circuits and constant depth circuits. They're kind of familiar to everyone, as opposed to some other circuit models that I've interacted with, like these fan-out circuits. So they're heavily studied and they have known limitations, but they're kind of very complementary. So Clifford circuits create long-range entanglement and are classically simulable, but they can't implement magic gates. Whereas QNC0 circuits, they're the opposite. And so it's kind of like the techniques used for one really don't transfer for the other.
The QNC0 circuit's not classically simulable. I mean, I guess it's not in using stabilizer rank things, but if it's a finite depth circuit, I can usually simulate it.
So you can estimate small output observables, but you can't sample from the distribution output by the circuit. Yeah.
That case maybe that appears to be still, it's not really the Clifford hierarchy. Sorry, I was a bit.
Oh, is it related to Clifford hierarchy? No. It's totally different. Yeah. Maybe if Clifford hierarchy, the name Clifford hierarchy was already taken. I didn't think I should call it that. Yeah. Yeah, that is kind of confusing. Any other questions? Okay, so now I'll mention how this model unifies some of the constant time models I mentioned earlier. So here are the ones that I'll talk about. And here's the magic hierarchy. So we show that the magic hierarchy is actually equivalent to these fan-out circuits. And it's pretty straightforward to see that it's at least as powerful as constant T-depth circuits, because you can always just implement this layer of T-gates in one of these layers. We also showed that it's at most as powerful as these circuits with intermediate measurements and feed forward. Or more specifically, I mean so the circuit looks something like this. But actually, with a few caveats, these are all equivalent. So the first for T-depth circuits is recent work by Isaac Kim. He showed that if you give your constant T-depth circuit some quantum advice state that's independent of the input, it's actually equivalent to the magic hierarchy. So you can implement an arbitrary gate with Clifford and T in constant depth if you have some advice state, or he calls it a catalytic state. Is there a question?
So for this picture on the bottom right, you say Clifford on the top left, are you allowing in-circuit measurements, as long as they're Clifford operations?
I mean, officially here, there's no measurement until the end, but we can kind of do delayed measurement. But this is without extra assumptions, this is more powerful. But we'll have to make an additional assumption about what the classical circuit's doing to say it's equivalent. Yeah. So now that's what I'll say. This intermediate measurement, it's equivalent if you restrict the classical circuit to only be the only computation the classical circuit can do is compute parities. And maybe this is maybe you can see why Clifford circuits can also compute parity.
So the equivalence. Okay, so you have a hierarchy of classes by the number of routes, and it's throughout.
Yeah.
I guess.
So you can think of the magic hierarchy as a whole as the union over all K. Okay. But it's still K is always you're doing the union over K. But K is still always has to be independent of the input size n. So magic hierarchy is just all circuits that alternate a constant number of times. Yeah, it's a little bit, yeah. Yeah.
So when you put the TPP protocols formulated this way, order that's the power of 2 something, I would expect you maybe need other mod gates.
So for their implementation, what the only thing they really need to do is group multiplication for abelian groups. And so you can sort of like, yeah, you can still implement this with, like, this gives us, I guess, multiplication over Z2.
Yeah.
But we can, yeah, you can still implement like any abelian thing with, yeah, addition on 2. Oh yeah, so there's some like constant overhead. It's like 4. I think the highest it gets is like 4. Yeah.
So it's like 1 round, or yeah, so you have some plus number of rounds.
Yeah, exactly. So it's like, yeah, it's like, you know, depth D in a depth D circuit here corresponds to, like, you know, like theta of D here and theta of D, like, yeah.
Important in this non-abelian context that like GNC0 layers are geometrically local.
Is it, wait, can you say that again? In what context?
In like this TBV.
Maybe it is.
I don't think it is. I don't think there's an easy way to do it. It's non-local.
Is that how they stated it in the paper?
I think they stated it like, well,
Sorry, are you saying that classical control is not local?
even if you make the gates non-local, I think it's easy. I don't think it makes it easy to constant depth preparation.
I think you can, once you have 2D and Clifford or intermediate measurements, I don't know if the classical part has to be local, but once you have like 2D, you can do permutations and stuff. So in constant depth.
So you can simulate any local sparse thing.
Yeah, like locality isn't so important once you have, I mean, yeah, maybe like level 1 magic hierarchy. Yeah, like once you have like level 1 or level 2, like, yeah, with some overhead, you can always just permute your qubits. So, but I don't think this is true for 1D, but I think once you're at 2D.
About this thing doing bigger non-abelian groups, is the Q dimension important at all? Can you simulate any dimensional qubits? Formulate everything with qubits.
I guess I typically just think of like if the qubit dimension is constant, then yeah, I feel like everything is the same. Yeah. Okay. Okay, so next I'll move on to barriers. So if there's any last clarifying questions for the model, now's a good time. Okay. So yeah, now I'll talk about barriers to proving circuit lower bounds. So yeah, as I mentioned, there's this really nice result that says that, you know, if you prove a state preparation lower bound, you actually get a Boolean function lower bound. A priori, it's not clear like how these two things should be related. And that's not like, you know, we've been studying Boolean functions a lot longer than states. So this gives us a lot of information. So yeah, Rosenthal showed in 2023 that, you know, there exists some circuit U, here I've drawn it as U1 and U2. It's a fixed circuit such that for any quantum state psi, there exists like a Boolean function here. This is like implemented as like a diagonal gate such that this circuit produces this state. It's like exponentially small precision. which is pretty crazy. The only thing, like for any state, you can just slot in here a different diagonal gate and it will prepare the state, which is pretty remarkable. You know, so this tells us that like a lower bound for preparing the state psi implies a lower bound for computing the function f. You know, once you take into account the complexity of U1 and U2. And so in my paper, I show that to implement these circuits U1 and U2, you can actually do it in the magic hierarchy. And so psi cannot be prepared, if you prove psi cannot be prepared by the magic hierarchy, that means that this is the part that can't be prepared by the magic hierarchy. So you show that this function can't be prepared. Yeah. Oh, it's quite high. Like I think this maybe like 20 or something. No, I don't think it's sharp. Yeah, I'll get to like related numbers. But I think that's an interesting question to make it sharp. Yeah. And also the magic hierarchy can simulate classical TC0 circuits, these threshold circuits I mentioned. And so this implies that this would in turn imply that this function cannot be computed by TC0. And so, yeah, if you prove that you can't prepare the state in magic hierarchy, you know, this would be huge implications. And so, yeah, we can take like a more fine-grained approach on, you know, if you prove a lower bound in a certain level, is there, you know, I said if you just show there's no level, you can prepare it, you get a big implication, but does this kick in at a certain level? And so, yeah, that's what I have here. So, you know, I show that, you know, for example, if you prove that you can't prepare a certain state within level 62, then this gives you a Boolean function that can't be prepared or can't be implemented in depth 4 TC0. And this is the threshold where this big natural proofs barrier kicks in. Even below it, we kind of have like a ranking of how difficult it should be. Like even within this region, you get a depth 3 lower bound, which no one's done before, so it'd be a big deal, but you know, doesn't run into this big barrier yet. And down here, you know, you don't have any barriers, but it requires new techniques, any known barriers, I guess. But yeah, these are sort of my upper bounds, but you know, I don't know how tight they are. I would guess they're not tight, so I think it's a really interesting question if you could tighten them. Like, you know, if it was 62, that'd be super weird. And the takeaway is, you know, we should expect grave difficulty in proving lower bounds above level 62, but there's still a lot of room to play below. Maybe a more optimistic view would be, you know, maybe this is an approach to proving TC0 lower bounds, but I'm not sure where I stand on that. Yeah. Okay. So now I'll mention the lower bounds I managed to show it in level 1. And even that's sort of like overselling it a little bit. I actually only prove lower bounds for when it's Clifford followed by a low depth. Though afterwards, yeah, people have proved the other direction as well. Okay, so I show that you can prepare various states even approximately. So there's sort of two different like proof approaches I take. The first is the first category contains states like the biased cat state and the W state. And the second is applies to ground spaces of local Hamiltonians. So examples in this category are non-stabilizer codes with super constant distance, certain non-abelian anion quantum double models, and the Feynman-Kataev history state for preparing the cat state. All that matters is just that if you look at the overall like Hilbert space of your code, that it's the dimension is not a power of 2. So I guess that depends on, I think that depends on like the topology and the like size of the group, and it's, yeah.
Like what's an example of dense space?
I'm not totally sure, to be honest. Yeah. Maybe we could figure it out after, but
Those degeneracies are almost never balanced. Like only if you have like age theory,
Yeah, I mean, your requirement is that it's not.
Yeah. Yeah, my understanding is it's not common, but I had trouble with these papers, so maybe you can help me. Yeah. Okay. So in this first category, the proof is actually really simple. I can like go through it in this talk and you'll probably understand. It's based off quantum mutual information. And the second technique is, more specifically for proving lower bounds for codes. But what's quite interesting is it rules out preparing any state in the whole code space. Okay, and what are the ingredients? Sort of the main like general thing that both of these use is the rigidity of stabilizer states. So you can think of these circuits also as just like a stabilizer state, and then you apply a load up circuit. And we'll exploit the fact that various properties of stabilizer states can take only discrete values. So like the lower bound proofs contain like several steps where there's some notion of like stabilize, like rounding to the nearest stabilizer, and this ends up being very, very useful. Okay, so now I'll talk about the first technique, using quantum mutual information. So here's our system, and we have two regions of qubits. And mutual information is just the quantity telling us how much information does A have about B. So here's the like formal definition, but all we need to know is that the only thing we use is that stabilizer states have integer mutual information, and also that light cones restrict the spread of information. So what do I mean by this? So again, we have our light cones, and we see that the information shared between A and B is at most the information here shared between LA and LB. Now we can apply the same argument with the double light cone on LA and LB. So I'll like double the light cones now. And we see that, now the information between these two regions is at most information between these two regions. And so now what we've done is, oops, oh God. Okay, now what we've done is we have an upper and lower bound on the information between these two regions of this state. And we're going to force this state to be a stabilizer. We're going to suppose this is a stabilizer state. So how do we get this lower bound for this? So the example is a biased cat state. So suppose we start with some stabilizer state, and with the load up circuit, map it to this biased cat state with some bias alpha. Our second observation tells us that the information between these two regions is upper and lower bounded by information on this cat state. And a really nice property of this biased cat state is that for any two disjoint regions, the information between them is just the binary entropy function of alpha. And so we can choose alpha so that this is 1/3. And then this will make both the left-hand side and right-hand side 1/3. But our first observation was that this thing in the middle has to be an integer. And so yeah, that's a contradiction. Yeah. And there's a bit more work to make it approximate, but this is the main idea.
Single stabilizer state to make this argument. Once you have it for that single stabilizer state, you can apply it.
Wait, like I guess we didn't need to fix the stabilizer state.
Well, when you run a picking out.
Oh, so we're picking we get to pick this state. This is the state we're trying to prepare, which is the biased cat state. Yeah. But so this is this is stabilizer, so we know this has to be integer, and then we want to choose a state here that means that the upper and lower bounds preclude it from being integer. Yeah, no, yeah, worries. Okay. Okay, so this is the first technique. It's you know, quite clean. The second one is a bit more involved. So I won't be able to like, you know, convince you probably, you know, that you fully understand the whole proof, but I can try to give you some intuition. The key idea comes from this property that I call like the infectiousness of these circuits. And so the theorem statement is if you have some code has super constant distance, that's the ground space of a local Hamiltonian, then if there's one state in the whole code space that you can prepare, then these circuits can actually implement an encoding circuit for the entire code space. And yeah, I want to also highlight that Ziwen Liu and Futron Wei like independently discovered this around the same time.
Quantum code here, does that mean just like
Yeah, it's just a subspace. It's just some subspace defined by a local Hamiltonian where like you have this like recoverability property. Any region of size less than D, there's like a recovery map.
no constraint?
Yeah. Yeah, I mean, it's even like it's even more general, but this is sort of the most like way that's easier to understand again. And so yeah, like rephrasing this, if you can prepare one state, you can encode the whole code space. And this is really nice because, you know, it's kind of easier to think about like proving that you can't prepare a whole code space because, you know, like I don't know, it's kind of difficult to think of like, okay, I have this huge code space. How am I supposed to prove that like there's not even just one state I can prepare? But if you want to say you can't do the whole code space, that's kind of nice because, you know, the whole code space can have a lot of structure. And just one state in it, like seemingly it's not obvious that it would have just as much structure. And so I found this very surprising and unintuitive. Yeah. I guess like what I'll have on the next slide is like the same property, but specifically for stabilizer states, like you take out these QNC0 circuits, and then you can map just from a Clifford. This is Clifford, so then this has to be Clifford, and then applying this extra layer affects them both in the same way, I guess. Yeah, maybe like after. Yeah, I won't be able to like show the whole proof, so I'm not sure I can give enough convincing argument.
Sorry, maybe I'm misunderstanding, but if you have like a toric code, we can prepare like an encoded stabilizer state of that with a circuit, but we can't prepare like an encoded T state of that with the circuit and constant depth thing.
Yeah, okay, good point. So this is kind of a subtle point. So you can, just because you have an encoding circuit for a code space, it doesn't mean you can prepare every single state in that code space. But if you give it like if the input is the T state, then it will prepare, then the output will be the encoded T state.
But not having the QC0 before as well.
Yeah. Then if you had the QNC0 before, then you could. But yeah, so yeah, crucially, it doesn't actually mean that if you can prepare psi, you can prepare every single state, but you can prepare all of the logical, some basis of logical operators, and so you have like an encoding circuit. Yeah. Okay, so using this, we show that these circuits, we show that these circuits can't encode certain codes. For example, code spaces with dimension that is not a power of 2. And which I mentioned earlier, and sort of the intuition is because the only codes that these circuits can prepare that have good distance are just stabilizer codes where you rotate them a little bit. And stabilizer codes always have dimension that's a power of 2. You apply some unitary that's not going to change the code space dimension. And another example is your ground space of a local Hamiltonian with a state that has still a lot of pairwise correlations. And an example of this is this history state for the cat state preparation. And there's also an approximate version of this, which I'll just sort of throw up with the corresponding adjusted parameters. Now you just need that the Hamiltonian has a spectral gap. Okay, and so now to provide some understanding of this infectiousness theorem, I'll instead try to help us understand if we just want to prove it for stabilizer states. So here the statement is, you have some code that's the ground space of a local Hamiltonian, and your distance is larger than the locality. Then if one state in the code is a stabilizer state, then the code is actually a stabilizer code with like the same locality. So, which is kind of crazy. If one stabilizer state in your code, it's a stabilizer code. And okay, we'll actually like kind of rephrase this because it makes the proof more straightforward. And we'll instead define some code to be the subspace spanned by states that are L locally indistinguishable from some state psi. And that means that like on any region of size at most L, the reduced density matrices are the same. And if the code has, sufficiently high distance, then, if phi is a stabilizer state, then it's a stabilizer code. Okay, so now I'll try to sketch the proof for this stabilizer infectiousness. This is probably like the most technical part, so yeah, so sorry if it's too much, but hopefully it gives those who are interested enough of a taste. So we have some code, and it's defined as all of the states that are locally indistinguishable from phi, and it contains in phi, we suppose phi is a stabilizer state. Okay, then it's also in this other code that's the stabilizer code that's stabilized by all the L local stabilizers of phi, right? And we're going to show that these two codes are equivalent. So first, the first direction is kind of easy. All the states in C are locally indistinguishable from phi, so they must also be stabilized by all of phi's local stabilizers. Okay, so then it's clear that C is contained in this stabilizer code. So we can move that over. And secondly, we need to prove the other direction. So we suppose for sake of contradiction that the stabilizer code is not contained in the code. So, there exists some state phi prime that's in the stabilizer code, but not in C. And since this is a stabilizer code, without loss of generality, we can assume that it's a stabilizer state. And since it's not in C, it's locally distinguishable from phi. So there's some region where these two things differ. But we can write any stabilizer state, its reduced density matrix as a sum over all of its stabilizers that have its support contained in A. Yes?
Well, I guess this sounds very familiar to
Oh, really?
I mean, the idea here is like,
Yeah.
it's basically the same thing.
Yeah, I guess we're defining, we're defining the code to be the information convex set. Yeah. But I guess usually for this entanglement bootstrap thing, like there's geometric locality as well. I guess you could do that here, but you don't need geometric locality for this. Yeah, you can choose whatever you want your marginals to be. Like here I just say all subsets of size L, but you could do whatever you want.
Longer than the other.
Yeah.
Size L, but you're
Yeah, yeah. I mean, you can choose, like, I guess beforehand you can choose, like, what are the things you want to be consistent with, and then define the code accordingly. And this is kind of the same thing as, like, you know, if you have any Hamiltonian and you define, like, you look at its codes, its ground space, and if it has big distance, it's like equivalent to this. Yeah. Okay. Yeah, so if you take a stabilizer state and you look at its reduced density matrix, it's just a sum over its stabilizers on that region. And so, you know, we have this for both of them. And since these are equal, that means there's like, there has to be some stabilizer in one of them that's not in the other one. But, you know, phi prime they're both in this stabilizer code. And the stabilizer code is just defined as the local stabilizers in phi. So the stabilizers of phi is a subset of phi prime stabilizers. So that means that there must be some L local stabilizer of phi prime that's not a stabilizer of phi. And we'll use this as, and so, but yes, since phi prime is in the stabilizer code, sigma must commute with all of the stabilizers in this code. And so it's therefore like a logical operator. Yeah, so the sigma, so yeah, we basically, yeah, I guess the high level is we find some sigma that's in a stabilizer of phi prime that's not a stabilizer of phi, but since it's in this same code space, it has to be a logical operator. And so, but since it's size L, that contradicts the distance of C being greater than L. Yeah, okay, this is like the end of the math. Okay, so yeah, this is sort of the overview, and yeah, I think this proof is like really nice and short, but a little bit unintuitive. So yeah, yeah. Any questions? Okay. So next, I'll mention some results. Like I'm gonna sort of like change gears, and so like if you like didn't like this or you didn't follow it, then like maybe you can listen again now. So I'll be talking about a totally different approach, getting like lower bounds on magic from communication complexity, from a different paper. So here sort of the idea was like, okay, can we show some connection of the following? Say that, you know, we can lower bound quantum circuit complexity by communication complexity. So something like this is known classically, and it's really cool. But you know, the quantum analog doesn't just like naturally transfer over. And the communication model we'll consider is this like simultaneous message passing. So Alice and Bob are given some input, X and Y, it's classical. They do something to it, send something to a referee, Charlie, who then computes the function. And they want to try to communicate as little as possible with Charlie. And the quantum circuit model we'll consider is just Clifford circuits plus magic gates. And the Clifford will be free, but the complexity comes from the magic gate. So the number of gates or the depth. And so yeah, here I'll just state the result. So we show that the communication complexity, the size of these messages, is upper bounded by the number of magic gates required to compute F in a circuit of the form. So you can think of these as T gates, but really they can be any single qubit magic gate. And you know, this is kind of nice because you know you can then get communication complexity theorists to prove quantum circuit lower bounds for you, and you know there's no quantum in this picture here. Okay, so here's the theorem again, and you know there's applications for this. So we get linear. Oh yeah, I also mentioned there's some overlap with this paper with Gossett, Kothari, and Zhang, but immediately get linear lower bounds on T-count for implementing the Toffoli gate and the multiplexer gate. Multiplexer is just saying like one of the registers tells me like, okay, output what's in register X, and then you know you do a swap and output what's in the register with the address X. Okay, I'll do like a quick, quickish proof sketch. So it's pretty easy, actually, if there's 0 T-gates, it's a Clifford circuit. And equivalently, we apply the inputs to X and Y. Equivalently, we could apply the circuit to 0 and 1, or 0, the 0 state, and then there's some like Pauli error that Alice knows this Pauli error, Bob knows this Pauli error. We can commute it through, and we'll get, this circuit looks like this. And so we can equivalently write the circuit like this. But then in order to figure out f of x, y, you just need Alice and Bob to send the referee whether or not there's like an error, like what the Pauli errors are here. And so then the referee can, apply these corrections and compute f of x, or f of xy. Okay, so quickly I can go through when there's 1 T-gate, we do the same thing. You can push the Pauli errors through. But now, these parts don't commute through the T-gate. So we can keep commuting Paulis through, like they're going to be different Paulis, but they're still Paulis, and they're Paulis that Alice and Bob know. But then we still get stuff stuck down here. But we keep pushing it through, and we get this equivalence. And so all that we need to do is Alice and Bob just need to send, the 2 bits before the measurement outcome, and or the 2 Pauli errors before here, and also the Pauli errors that got stuck behind the T. The referee just implements this circuit and can get f of xy. Yeah, I went through that kind of quickly, but there's one more result that I won't prove, I'll just state, and we'll have like unfamiliar communication complexity stuff on it. So don't get too overwhelmed, but here's a different computational model where now there's quantum messages and a quantum entanglement. And we show that you can convert a protocol of this form to one with classical messages, and they satisfy some privacy requirement. And this conversion has low overhead if C has low T depth. And so what this tells us is if you get the quantum advantage between these two, so if you say like some function has a quantum advantage, the quantum protocol is much, much more efficient than this classical one, then this tells you that this referee's T depth has to be large. So this gives you a T depth lower bound from like quantum advantage in communication complexity, which I think is like pretty cool. But maybe I shouldn't say that, but yeah. So like just for reference, the best known lower bound on this communication model is exponential in n. So this could give us like n linear. This would give us potentially like linear depth lower bounds. Yeah. For here, no, it's just unitary. Yeah, it's just Clifford and T gates. That's all. Yeah. Okay, the previous thing I had for T count was that you just need to be able to compute the function to within error that's like less than 1/2. So approximation's fine there. For this one, I think you need perfect, yeah, there's no problem. Yeah, you need perfect correctness. Yeah. Okay. So yeah, here's the summary. I won't throw more things at you anymore. And I'll throw up a bunch of future directions. There's a few different categories. You can look at whichever ones interest you. So stronger circuit lower bounds, learning, what's the complexity of learning these circuits, the tightening the connection with classical complexity, and finally, like interesting questions in condensed matter. I bolded some of them in case you want a few to look at that might be interesting. Yeah, maybe in particular, condensed matter Hamiltonian complexity might be interesting to people here. But yeah, thank you. Yeah, I think I'm like at the hour now, so I should stop.
Okay, great. Thanks for a really interesting talk. Maybe we can have one question if someone has a burning last question. There were a lot of questions during the talk. Yeah, Eric.
Or even anyone else's question. So I'm curious about these like analogs of TDB where you're not trying to necessarily if you formulate the problem that way, do you run into these?
Like if you prove a statement that's like, oh, if you somehow can prove like, oh, there exists like if you prove only the existence of, oh, there's some state in the subspace that I get a lower bound for, then you don't immediately get natural proof. Like if you don't have an explicit state, you don't immediately get one, but you have to be careful that from this you can't figure out an explicit state. Right. Yeah, but you could still hope for a non, like a, yeah, like this is kind of called like a non-constructive lower bound, like or the existence of a lower bound. Yeah.
Great. I think we should thank Natalie again.